something.
So the trade-off he's talking about there, for a random number generator, for a given period, you have an associated state vector. So if you want a random number generator that has a very, very long period, that means you're going to have a progressively larger and larger and larger state vector. The problem with that, for something like Mersenne Twister has a huge, huge period, but as a result of that, the state vector is about almost a kilobyte, or actually it might be two kilobytes for the state vector. That, if you put it onto a GPU, would mean that for one instance of that random number generator, you would need a huge fraction of your shared memory just for the random number generator, leaving you almost nothing for the rest of your simulation. So there has to be a little give and take in terms of the period that you need for your random number generator, or else you have to use an approach where you generate a massive block of random numbers in global memory and consume them in a separate kernel. So this is a point of contention for anybody that does Monte Carlo. Your choice of random number generator is critical in terms of your resource usage on the GPU.
Why can't you generate the random numbers, put them in global memory, and allocate them in chunks?
You could, and people do that.
Okay.
And if you need a super long period random number generator, or maybe you're doing for every random number you read, maybe you're doing a few thousands of floating point operations. In a ratio like that, it makes perfect sense. But in Andrew's simulation, correct me if I'm wrong, the ratio of the random numbers generated versus the other work that's being done, the random number generation is maybe 30% of what he's doing. So the rest of his work, there isn't that much else. Once he's got the random numbers, he's picking which transitions to make. He's actually doing a little bit of array indexing here and there, some flops. But that random number, they're being consumed at a very high rate in his code. And so that approach for him would result in way too much global memory accesses.
I haven't read a lot about this, but if you've got a kilobyte of state, you should be able to produce a kilobyte of random data for every iteration on that state. So I'm not sure exactly what the Mersenne Twister is doing, but if it's only extracting off a little bit, there could be a way on a GPU to, in parallel, generate a large number of random bits simultaneously and use those in parallel.
Yeah, I mean, that would be another trick, is use some of your other shared memory that's not actually part of your random number generator to feed your random number generator with more bits of data that are changing in some uncorrelated way, hopefully. That's another trick you could use. Kind of like on the host, sometimes they use various machine system timers and things to help feed the random number generator to prevent it from being correlated with anything in particular.
Or you use the good random number generator to seed cheap random number generators on each of the threads.
I'm surprised because random number generators are something that are so
fundamental.
Yeah.
And you'd think, why didn't they have I don't know, but it drove all of us crazy. Zan, I think you made the comment, Zan's students spent a fraction of their time beating their heads on the table, coming up with reasonable random number generators that they could use. This is their later work. They've been doing this for a few years now. When they began, there were basically nothing that they could use. And it's very frustrating, and I don't know where all the random number generator experts are, but they haven't caught on to GPUs yet. So they're all of us are having to do it ourselves.
Every time there's been a new platform, computing platform, it's the most fundamental feature that should be there. And it's somehow they just make the machine and, oh yeah, how we need that.
They put the Earth function, but they didn't put it.
I mean, Kepler. Right?
I'm done ranting.
Sounds like we have a good lunch topic. Okay.
So I need to move quickly here, but obviously, we need to avoid bank conflicts for these states which are stored in shared memory. So instead of having them, access a state which is sort of stored linearly, we can have them interleaved like this, which will improve the bank conflicts. And I believe this is going to get even better when we start moving to the Fermi hardware. there is an alternative implementation for large systems, which I've more recently been working with, in which, notwithstanding the fact that the entire Gillespie algorithm is really not parallelizable, it is possible to parallelize calculation of propensities. Propensity calculation, if random number generation is 30%, propensity calculation is basically 65. It's the vast majority of the rest of the algorithm. So we could parallelize that, and in this case, for systems in which we had a very large number of reactions, we can allocate one block to being one cell, as opposed to being one thread to being one cell. And then we can allocate each thread in that block to calculating the propensity of an individual reaction. That really takes away the use of constant memory for the rate constant matrix and the stoichiometry matrix, because now the different threads are all accessing different elements of the stoichiometry matrix at the same time. You totally lose that broadcast, so you really need to move this into shared memory, but it becomes less of a concern because now you have a lot more shared memory to work with, since you only need to store one state vector and one propensity array for the entire block. So this is an alternative implementation.
So why don't you tell them how many reactions you've been able to do?
Well, I've done many hundreds of reactions this way. And typically you want to move into some sort of sparse matrix for the stoichiometry matrix, and you do that else, because most of it, if you look at the S matrix for the Michaelis-Menten system, it's relatively non-sparse, but when you're talking about hundreds of reactions, this is a very sparse matrix, so you're going to want to move into more of a sparse matrix storage. Okay, so this just gives you a good idea of what I mean between stochastic and deterministic. This is the same plot as before, the deterministic solution for the Michaelis-Menten system, and here is the stochastic solution, or set of solutions, I should say. So you can see that when we run on 2,000 executions, we get a wide variance in the way each thread sort of chooses or randomly decides to solve this set of reactions. And this level of variance, although it's not, in this simple system, it's not clear how important that is. When you're talking about, a transcription factor, did it bind or did it not bind? Suddenly, is a gene expressed or is it not expressed? And maybe that gene does something really important. And so this becomes very important when you're talking about cells. So now just a quick slide on performance. My implementation of the algorithm, I achieve a 35 times speed up over my own CPU implementation. Liam Petzold published a paper in 2009 in which they presented 200 times speed up. However, this is not the clearest plot. You can see that the green is my CPU, and so we have num executions here, and the amount of time it takes, and their CPU, which seems to be a lot slower. So it could be that we just get, maybe I'm running on a faster CPU, maybe their CPU implementation is not as efficient. But, so we'll say that the speed up in this range is between 35 and 200. Okay, so moving on to the second part of my talk, which is the spatially resolved stochastic simulation. So remember that the Gillespie algorithm assumes that all of these biochemical reactions are all equally probable anywhere in the system. We believe, and evidence is increasingly showing, that that is not true in real life. The cell is not well mixed. The cell is very crowded. E. coli, which is the model organism that most people use to study these sorts of things, is about 2 microns long and 0.8 microns in diameter. It has, between 18 and 37,000 ribosomes, 2 million proteins, 18 million small organic molecules, and a 4.5 megabase chromosome, all of which are not evenly distributed throughout it. 30 to 50% of the cellular volume is occupied by molecules other than water. And so this gives you an idea of how packed that is. This is, which I'll get to, this is one of our lattice packing simulations where we've actually packed the volume of the cell, this is just a subset of this, to 30%. It doesn't look much like 30% when you just look at the plot, but as you take slices and slices, you can see that there are small regions of space within which other molecules can diffuse and react. But it is hard to see how anything could be evenly distributed throughout this volume. And we use size classes and populations which have been described from proteomic studies to actually fill the cell full of these obstacles. So, what we're doing here is a lattice-based diffusion model. So we simulate we place a lattice in GPU memory we fill it up with obstacles, we place particles on the lattice, and we allow them to move. Traditional lattice diffusion methods will have a particle randomly moving from site to site on a lattice with a spacing lambda. And then basically at every site in which a particle finds itself, 3 random numbers will be generated. It will decide if it wants to go up or down, left or right, back and forth, or some combination, and it moves. And it can be shown, though I won't show it here, that if the probability of moving in any direction is p, and the probability of staying is p naught, then this model obeys the standard diffusion equation, which is what we want. And importantly, if we know the diffusion coefficient of the particle we're trying to model, we can calculate the probability that it will move during a particular time step, given a lattice of a particular resolution. There's a problem with this on the GPU, or at least the current GPUs. Well, I'm not quite there yet, I guess. So basically the idea is you load a block of lattice sites into GPU memory. They won't all fit. You choose the direction each particle is going to go, and then you update the set, you write it back, and then you load the next one. Obviously, each calculation is limited in terms of the amount of memory you can access. Shared memory is very limited, and even though Fermi is now quadrupling the amount of shared memory, we still don't expect it will be enough to actually handle as much as we would like to. Because processing a 3D block of the lattice requires many apron sites. And an apron site is, and if you think of this as these are slices through a cube, all of the grayed out blocks are the apron sites, which we're not actually calculating for, but things might move into them. So we have to load. And as shared memory, as that block increases, the apron sites actually become a significant percentage of the shared memory. So this limits us a great deal in actually trying to load in a 3-dimensional block of sites all at once. To solve this, we switch to a 1D model. In this case, each particle will diffuse independently in each direction. And so we'll basically load in a block of sites and choose where each particle is going to go in 1 dimension, and update and save that, and then load in a new set of sites, choose where the particle is going to go in the other direction, finally choose the z direction, and as a result, we only have to load in a much smaller region of the lattice at once. And it can also be shown that if the move probabilities are isotropic, that is, it's not more probable that a particle will go up than it will go left, then it still obeys the diffusion equation in a slightly different form. But we can still calculate the probabilities for each direction given a diffusion coefficient, a lattice spacing, and a time step. So this is just a simple test, free diffusion on a lattice, just building a cell, putting a bunch of particles in it, allowing them to flow around, and measuring how far they've gone in a certain amount of time. The particle distribution after some specified amount of time should be Gaussian. And in here, the theoretical are the lines, predictions, the circles are the actual movement. You can see that they agree virtually perfectly with what we want. So we're seeing correct behavior of diffusion of particles on the lattice. But our ultimate goal is really to move to long-term whole cell simulations in which we pack that cell full of obstacles. We give particles, we distribute the particles within the cell, we allow them to diffuse, we allow them to react in accordance with this Gillespie algorithm, which I talked about in the first part of the talk, and analyze the resulting stochastic behavior to see if we can model some of the the observations that have been made in many recent papers. Okay, so before I get to the example of what we're doing here, I'll briefly talk about how to measure the performance of this. We didn't write a CPU version of this. It's a lot of work, so we didn't.
And why write a slow code?
Yeah. So I can't tell you exactly how much faster the GPU algorithm is than the CPU version. We can say that moving to more and more advanced GPU hardware, we do see a significant speed up, and we expect this speed up, I believe, even without modifying the code, we